Hello, guys. This is Devdut Mitra from Chemistry A to Z channel. After a long interval, again I have came to make you learn some graphical problems from the second chapter of our syllabus, that is structure of atom. The first one, you see the question: variation of radial wave function r against distance small r is given for 2s orbital. So you have given four options, four graphs. You have to select the incorrect one. So what will be the correct one? It will be D, is not it? It is answer D. Just a moment. It will be answer D. Why this is graph gets the correct one? For 2s orbital, we may calculate the number of nodes n minus L minus 1, that is radial node, and you know for s orbital angular node is 0, because s orbital is spherically symmetrical, it has no direction property, so only we have to calculate radial nodes. So this is the formula of radial nodes. n is equal to 2, for s orbital L is equal to 0. Okay, therefore number of radial nodes for 2s orbital is 2 minus 0 minus 1, that is only 1. And you see incorrect one. So in A, B, C there is a node. Here it is node, right? It is a node. It is a node. But in this case there is no node. That is why our answer should be D. Okay. Now let's go for second one. I hope that you understand this one. It is very easy. This type of question, if you have to face like this question, then you have to find the number of nodes present in the corresponding orbital. The next one, problem says, which of the following radial distribution graphs correspond to L is equal to 2 for hydrogen atom for the least value of n which L is equal to 2 is allowed. So what do you think? Which graph should be the correct one? Huh? Okay, now find the number of radial nodes. Again, number of radial nodes which one? It will be 3 minus, that is n minus L minus 1. So here 3 minus 2 minus 1. So 0. That is no nodes. Okay. L is equal to 2. When L is equal to 0, it represents s orbital, right? L is equal to 1, then it is p orbital, okay? And when L is equal to 2, then it is d orbital, and L is equal to 3, then it is f orbital. You understand? So here the question says, which of the following radial distribution graphs, correspond to L is equal to 2 for hydrogen atom for the least value of n. So least value of n, L is equal to 2, the least value of n should be 3, right? That is why I am writing 3 minus L value of L is given 2. According to the formula, it would be n minus L minus 1, that is 3 is the least value of n for which L is equal to 2. 3 minus 2 minus 1, so we get the result 0. Therefore our correct option is which graph? Option C, because here is no node. Okay, I hope that you understand. Is not? Okay, let's go for question number 3. Here it is a large question. It is a big one. The wave function psi NLML. You know, n is the principal quantum number. L is the azimuthal or angular quantum number. ML is the magnetic quantum number, right? And MS spin magnetic moment quantum number, spin quantum number. So here psi represents the wave function of an electron as well as an orbital, where the probability of finding electron is maximum. So psi NLML, it is a mathematical function here whose value depends upon spherical polar coordinates, that is r theta phi of the electron, and characterized by the quantum numbers principal, azimuthal and magnetic quantum number. Here is the distance from the nucleus. Theta is co-latitude and phi is the azimuth. Okay, in the mathematical functions given in the table, Z is the atomic number and Bohr's radius, that is 0.53 Armstrong, is A0. So you have given, there are 3 columns. Column 1 for first 1s orbital, the expression is given as follows. What is this? For 1s orbital, we are given psi NLML directly proportional Z by A0 to the power 3 by 2 e to the power minus ZR by A0, right? It is given in column 2. See, for 2s orbital it says only one radial node, and in column 3 the corresponding graph for psi NLML with respect to radial function r, and it is the distance from the nucleus, separation from the nucleus with respect to A0. The graph is shown here as follows. Okay, and also gives 2pz orbital, the expression of psi NLML and 3D z square orbital. XY plane is considered to be a nodal plane where the node may present here. Okay, so there are three parts of this question. For helium ion, we have to choose the only incorrect combination. Which one? For A, I am doing here question number part A. The option 3, that is for 1s orbital, no angular function should be present. Okay, because 1s orbital has no directional property. Therefore, it is for A. So the incorrect answer helium ion, the only incorrect combination is no angular function should be present. For B, this should be R. What is R? Probability density is maximum at the nucleus. This will be the wrong, that is option B here. Okay, here R says that probability density is maximum at the nucleus. How can it be? It cannot be. So this is the incorrect combination. And part B, it should be, part B says that for hydrogen atom, what is the only correct combination? So it would be D, that is here. It is the correct combination. Why? Because you see, correct combination D 1 S for 1s orbital. We know the relation here. We have already written psi NLML directly proportional Z by A0 to the power 3 by 2 e to the power minus ZR by A0. Okay. Therefore, energy needed to excite an electron from n is equal to 2 to n is equal to 4, we can write delta E 2 to 4, that is lower to higher, is equal to 13.6 into z square into how much? 3 by 16. It is 1 by 2 square minus 1 by 4 square. So it would be 13.6 into z square, and that is 4 into 16, 4, 16, 4 minus 1, that is 3 by 16, right? You understand? 13.6 z square into 3 by 16. Similarly, energy needed. Achha, I am doing on the right hand side, not here. Energy needed to excite an electron from what this says, n is equal to, just a moment, yeah, it is the question. Energy needed to excite an electron from n is equal to 2 state to n is equal to 4 state is 27 by 32 times the energy needed to excite an electron. It should be an electron from n is equal to 2 state to n is equal to 6. Okay. Therefore, sorry, from n is equal to 2 to n is equal to 6, we can write delta E 2 to 6, that is again 13, the same formula, z square into 1 by 2 square minus 1 by 6 square. So it would be 13.6 into z square, 8 by 36 electron volt. We have to write here electron volt, yes. Therefore, delta E 2 to 6, that is it will be 4. It will be 2 to 4 into 16 by 3. After eliminating 13 the common part on both sides, 13.6 and z square both can be cancelled out. 16 by 3 into delta E by 2 to 4 is equal to 36 by 8 delta E 2 to 6. So delta E 2 to 4 is equal to 36 by 8 into 3 by 16 into delta E 2 to 6. So what will we get? We get 9 4 27 by 32 delta E 2 to 6, that is delta E 2 to 4. Therefore it is proved. It is proved. Which is the statement where it is a trace statement. Energy needed to excite an electron from n is equal to 2 state to n is equal to 4 state is 27 by 32 times the energy needed to excite an electron from n is equal to 2 state to n is equal to 6. Okay. Therefore option B, here D1S, it is D1S, it is the correct option. Now we move to option C. Option C, for the given orbital in column 1, the only correct combination for any hydrogen-like species. It is the. Now we go for C here. C, which number? Question number 3. Question 3 part C. I am making you to see. Here C for the given orbital. What about A? A, what is A? Where is A? Here it is. I am talking about like here. This one. 3 of 3p. Now see 3 of 3p. That is 3 relation with p. It is incorrect. Why? Because 3 I am writing of p is incorrect. But why? Because the probability density for 2p at nucleus is 0. Okay, so it is incorrect. You can check it. See A, 3 of 3p, 3 of 3p, probability density maximum of the nucleus. It is wrong. Here I am writing the probability density for 2p at nucleus is 0. This is A. And for B, you can check here B 1 2s 1 2s. Now see 1 2 s 1 2 s. So it should be incorrect. Parts here A, parts here B. 1 2 s, it is also incorrect. Why so? Because you know 1s orbital has no radial node. Because 1s orbital has no radial node, right? That is why it becomes incorrect. Part C, see what it says. Part C, here part C, 4 see, check here, 4, that is it is 4 R. 3D z square orbital, xy plane is a neural plane. No, it is wrong. Probability density, it must be wrong. C4 4R is another incorrect, because dz square has no nodal plane, rather it has nodal cones. You know, it has only nodal cones. I can make you see the nodal cones of dz square, like here. Say I'm drawing in this case. In just a moment. Here it is z axis, and the dz square should be here. Like this, and it is okay, and the nodal plane it is one nodal plane, and nodal cone, not plane, sorry, it is nodal cone, looks like this one, and it is also another nodal cone. Y-axis, x-axis, like this. So it has no nodal plane, nodal cones. These are nodal cones. Okay, it is nodal cones, not nodal planes. So you understand? Therefore D should be correct one. But why? I am making it explain to you. D, what they give? You see the table? D is given 2 2p. 2 2p. Okay, 2s orbital, 1 radial node, relate to p. It is okay. 2 2p. It is the correct one, correct option, because correct option because 2s orbital has one radial node. Okay, that is n minus l minus 1. Do the same. You got 2 0 1, so it is 1. So the correct option is in this table is D. For part C, D is the correct option, right? Now In the next problem, here it is says that if P is the probability finding the 1s electron of the hydrogen atom in a spherical shell of infinitesimal thickness dr, like here. If you want to check it, I'm doing here. It is a spherical sphere, and if this one thickness dr, and if it is nucleus, then r is the radius and dr is the thickness. Okay. The volume of this shell is 4 pi r square dr. Here it is, volume of the shell. The qualitative sketch of the dependence of probability of finding the 1s electron on R should be which one? Now we can calculate. It is question number 4. Here I am making it question number 4. It is question number 4. Just a moment. Make some divisions. Either we may confuse. Okay. Understand? Question 4. I am making the division from 3. Question number 3. Here it is question number 3. Question number 4. Now we may calculate. For 1s orbital, the radial part of the wave function is psi r. It is the wave function, radial wave function. The formula was, I have written here also. Where? Here, Z by A0 that is, it should be look here. Z by A0 to the power 3 by 2 e to the power minus ZR by A0. Okay, it is for 1s orbital. So the probability of finding an electron, the probability of finding an electron in a spherical shell of thickness dr, here it is thickness at a distance r from the nucleus that is p psi r square it is 4 pi r square dr. So we may write that is 1 by A0, because Z is equal to 1 for hydrogen atom, 3 by 2 e to the power minus R by A0. And Z is taken as 1 for hydrogen atom. Okay. So it would be 4 1 by A0 3 e to the power minus 2r by A0 into 4 pi r square dr. Therefore we get 16 pi r square 1 by A0 to the power q e to the power minus 2r by A0 into dr. You understand? I hope you understand. So the probability of function P is 0 at r is equal to 0, is not it? And r is equal to infinity. Okay. Therefore the graph should be like this. No, it should be so. It is option. What they give? Option C. Here it is, guys. Hope you understand. Option C. Correct option is C. Understand? This is R. Zero to R. That is why I have here it is 0 and it is infinity. R is equal to infinity here. So probability of finding electron is 0. Okay. Okay guys, we have discussed few questions based on graphical problems. If you understand, I hope that all of you understand how to solve these problems. In our next video we will do more and more such type of graphical problems based on structure of atom, which few of them already came in 2020 to 21 advanced day problems like here the question number 3, it has already came in 2000, either it would be 2020 or 2021. So we will do many more problems like this on the chapter structure of atom, graphical problems, in our next video. So if you like this type of video, please share, subscribe and make likes to my videos from Chemistry A to Z channel. Okay, goodbye.